So today, I'm here to play with a fun, neat feature in Proxmox Virtualization, Single Root I/O Virtualization, or SR-IOV. So, SR-IOV is a technology that allows a PCI device to be passed into a virtual machine, but not just the whole device, you can pass a slice of it. So if you've heard of that before, you've probably heard about it from Wendell. You guys watch Wendell? Anyway, he's talked about it as like the holy grail of graphics virtualization, passing a single graphics card to multiple virtual machines. And that's not what I'm doing today at all. I'm doing the same thing, but with network cards. So many network cards support SR-IOV out of the box. It's super easy to set up in Linux, and I'm going to see if I can get a performance advantage in Proxmox for my VMs, rather than just using the Proxmox default Linux bridge. So if that sounds like a good topic to you, then come along on this adventure. But first, this video is brought to you by Ugreen power banks. If you're on the go a lot, you might need some power to help you keep up. Meet the Ugreen Power Bank, your portable power companion. I'm going on a trip this weekend, and I'm only bringing my backpack, so I gotta decide what I can bring and what I can afford to power on my trip. Now obviously laptop and phone are a must, but am I gonna be able to power both of these for 6 hours if I'm watching YouTube the whole time? Since I have a pretty big bag, I can probably fit the larger 20,000 milliamp hour Ugreen charger in my bag, along with all my clothes and my laptop and all my cables and stuff like that. In fact, this nice column design actually fits in the water bottle holder here, so I can keep it with me, easy access. Maybe if I'm traveling a bit light though, the smaller sibling, the 12,000 milliamp hour, would be a better choice. So between hotspotting on my phone, watching stuff on my laptop, and charging my headphones, so that's a lot of stuff to charge. So it's great that this thing has 3 ports, 2 Type-Cs and a Type-A. And each of these are independent too, so you can get 130 watts combined, split up across those ports. Smaller one has 1 Type-C and 1 Type-A. Again, they're separate ports. Now, if I'm unable to plug in for longer than I expect, this big guy here can charge an iPhone 15 4 times over. You can also rapid charge it up to 60% in under 30 minutes. Or I could fully charge my laptop and my iPhone once each. I'm taking a train, so it's not an issue for me. But it is also airline approved if you want to fly with it. It's got a handy screen that shows the battery status and if it's charging or discharging, and also smile at you sometimes. So if you're interested in the 130 watt, 20,000 milliamp hour, or the smaller brother, the 100 watt, 12,000 milliamp hour, get yours in the link below. Now back to the video. So here's the hardware I got for this setup. That is my box PC. It is in fact an ASRock B450M Pro 4 motherboard. It has a Ryzen 3400G APU, that's Zen 1, like a Raven Ridge generation. And the card here is Mellanox Connect X4, which is a 25 gig dual port card. And over here, I have the benchmark system connected over 10 gig to an Intel X520 direct attach card on the PCIe riser from the Minis Forum MSA1. So all the SR-IOV today is happening on the Mellanox card. I'm not doing any on the Intel cards. That said, the instructions are exactly the same. So here's my test setup here. I've got Proxmox running. I've got nothing running at all on Proxmox. Everything is shut down. I do an iPerf test to a IP address. I'll do a 120-second test and kick that off. So I'm getting about the 10 gigs I expect, which is fine. So maybe a few graphics would make this make sense. So in the Stone Age of virtualization, we had real physical computers. And every time we had to do a job on a computer, we would get a real physical server in a rack somewhere, install Linux on it, or Windows 98, or Windows NT, or whatever you're using back then, Solaris, and run that as our workload. And that real physical computer had real physical hardware, like a CPU, memory, network cards, graphics cards, things like that. You could put cards in the system, that's what they're called, cards, to do stuff. So then some smart people invented virtualization. What if we got a really big, powerful server, we took all these Solaris, Linux, Windows installs and put them into little virtual partitions within our big fancy server. So in modern day virtualization, we have the CPU, which executes instructions and stuff. That is emulated in hardware by AMD or Intel. They support things like nested page tables. All of the instruction pipeline is actually done in the real CPU and hardware. But everything else is kind of faked. We have to fake it. And that's where QEMU comes in. So specifically in the context of networking, on a real system, you would have a real network card with a MAC address. It would speak Ethernet, if you're using Ethernet and a Wi-Fi, but whatever. Then the operating system does IP layer 3, IPv4, IPv6, that kind of stuff, etc. So in a virtual machine, we need to fake the virtual machine into thinking it has a network card with a MAC address that is Ethernet. And so we do that by either emulating a popular real network card on emulated PCI Express. That's where you get things like the Intel E1000, that's wildly popular to emulate. Or we create a fake PCI Express device that's tailored to be optimized for virtualization. And that's where you get things like VMware VMXNet 3 or Red Hat VirtIO. Or we can take a real PCI Express device from the physical system and give that up into the virtual machine, so the virtual machine has control of the physical device instead of the hypervisor. So again, in the context of networking, we have a bunch of virtual machines in our Proxmox system. They need to talk to the internet. So we give them all virtual network cards. Now they need a network switch to connect all these VMs together. So Proxmox, of course, runs a virtual network switch. This is the Linux bridge that we configure in Proxmox networking. VLANs, bridges, and bonds up here. So now we have a physical network card on the Proxmox system talking to a virtual network switch run by Linux, talking to a virtual network card on the virtual machine, talking to the virtual machine. So with SR-IOV, basically that one network card splits itself into several bits. So this Mellanox I have can do 127 of them. So now I have 127 PCI Express devices I can pass through to individual virtual machines. And each one of them gets its own real ConnectX-4 network card. And the network card itself is running the virtual switch. So the network card now has a real 25 gig connector. It has the physical function, which is what Linux on the host uses to configure the card, configure the 25 gig link, things like that. And it has 127 virtual functions. And these are more limited in what they can do, and they can only pass traffic. They can't configure the card. So we give these to the VMs. Now we have 128 network cards, plus the real 25 gig physical interface, talking to a virtual switch on the network card. So now we've offloaded the work of emulating the network card and offloaded the work of emulating the network switch both onto the hardware of the network card. And it's very good at these things, so it's very efficient and very fast at it. So the question is emulating this high-speed networking actually saving us anything? Are we actually saving any CPU time on our host at the range of 10 gigabits? Or do we have to be going much faster for it to matter? The other thing is, with LXC containers, this is flipped a bit. So LXC containers run in a namespace within Linux. This is the same feature that Docker uses and other containerization systems use to isolate processes. They have their own file system, they have their own network. But they're still running under the same kernel, so we don't actually have to emulate a network card at all. We can just take the same network card, we still emulate the virtual switch, but we can just take more namespaces and port them into the virtual switch really easily. So the overhead there is a lot less, we're not emulating any hardware, so maybe it doesn't matter as much for LXCs. Now, yet another wrinkle into this is that a lot of packet processing has to be dealt with on a per packet basis. So for every packet we have a 1500 byte MTU, for example. So essentially we take megabytes or gigabytes of data we want to transmit. You have to break them up into small packets, give them each a header, calculate the header checksums, all that kind of stuff. Then we file them out through the network card. They go out across the network. When they come back, they have to get reassembled too. And that takes work. But modern network cards do a lot of that for us. So a lot of network cards nowadays do TCP segment offloading. So essentially, if you want to transmit, say, a megabyte over TCP, you would have to break that up into 14 60-byte chunks, add in the 40-byte IP header for each one, calculate the checksum, all that good stuff. And for a lot of modern network cards, you can give them more than one packet worth of data, and they will split it into the MTU size in hardware in the network card. And so Linux's entire network pipeline deals with these packets that are larger than normal. So you might have a TCP packet, for example, that's 2 packets stuffed together with one header, and when it gets to the network card, it splits them back into 2. So that way it has to do half the amount of packet processing. But when you use Linux bridges, that gets carried through the entire system and the packets never get split and reassembled. So if I'm sending data between 2 virtual machines within the same host, it might be able to carry them as, say, 65K, or 64K, I guess, 65535 bytes, and never break them apart into smaller packets, even though the MTU claims to be 1500. So, for example, the VirtIO NIC might tell the guest operating system it can handle 64K chunks, and it'll segment from there. But then when it actually does the packet processing in the kernel, it will never segment them. It'll just pass them over to the other NIC unsegmented. So that's a bit of an optimization here that also affects this testing and this load. So anyway, I'm running these tests on my system. I'm running them at 10 gigabits, so I'm running over real 10 gig hardware. and I'm limiting my internal loopback test to 10 gigabits so that the bandwidth doesn't go through the roof. I'm trying to see if there's any single thread bottlenecks in any of these adapters, and I'm measuring this with the Linux CPU load piped over to InfluxDB. I have a video on that tutorial as well. So let's see what happens. So I got this small VM here, SR-IOV test. It's not massive, 4 cores, 1 gig of RAM. I'm going to give it a new network device. Put it on bridge 1, because that's the one I've been using for testing. And we're going to start with Virt.io. So data. So for the remote tests, I would expect to see 9.3 gigabits per second in iPerf, because 10 gigabits is the layer 1 signaling rate. There's layer 2, and layer 3, and layer 4 overhead in that. So 9.3 gigabits is what I would expect at TCP. Now, not all of the virtual NICs could achieve that. So they were essentially running full out if they couldn't achieve 10 gigs. For the loopback tests, I was going from the virtual machine to the Proxmox management interface. So this would be essentially half of a round trip between 2 VMs. Now, this load does include running iPerf itself on the Proxmox host for the local tests. For the local tests, I limited the bandwidth in software to 10 gigabits in iPerf. So iPerf won't try to do more than 10 gigabits. However, I also measured what the bandwidth is capable of for us to look at also. Now, these numbers are in CPU units, so Linux records this as essentially the amount of time one CPU would be occupied. The system has 4 threads, so an 8 would be fully loaded on this system. Lower is better, obviously. So in Debian, the E1000 and the VMXNet3 are notably worse than both the Virt.io bridge and the SR-IOV Mellanox card. So if your traffic is primarily remote, it looks like the SR-IOV is a little bit better. And if your traffic's primarily local, it looks like the Virt.io bridge is a little bit better. But in any case, VMXNet3 and E1000 are definitely worse. Now as for throughput, the E1000 and the VMXNet3 were both not able to reach 10 gigs. Not really a surprise. I think both of them are limited to a single thread in QEMU. So Virt.io and SR-IOV were both able to blaze past 20 gigabits internally, so that's nice to see. So on Windows, I installed the Red Hat Virt.io drivers for Virt.io. I did not install any drivers for VMXNet3 because Broadcom wouldn't let me download them. So the VMXNet3 performance was god-awful. I know it looks like the VMXNet3 is using like no CPU load, but it's also not even able to hit 1 gigabit, so it sucks. But basically, E1000 is better on Windows than it was on Linux. Virt.io is still pretty good. SR-IOV is notably better if you're doing remote I/O, not really a difference if you're doing local I/O. And again, local I/O would be a similar path to what 2 VMs might take to each other. Not exactly, but keep that in mind for your traffic patterns. And for Windows throughput, VMXNet3 was absolutely awful again. It barely hit 2 gigabits local and like 800 megabits remote or something terrible. Virt.io and SR-IOV were both able to hit 20 gigabits, so that's about what the limit seems to be for both of these guys. It's a 25 gig card and it's only a quad-core CPU, so I'm sure with higher-end hardware you could push these both much more. Now the really interesting one to me was LXC. So it looks like this graph looks pretty drastic. But notice that this graph only goes to 0.7, and my last graph went to about 2. So LXC networking is much more efficient than VM networking in general. So essentially for this test, we're not emulating hardware, so it's are we emulating the Linux bridge or not? Are we doing bridging in hardware on the Mellanox card or in the Linux bridge in software? And again, I think it's really hard to say anything about these because the idle load of the system is like 0.2 to 0.3, and my numbers aren't that much higher than it, so any sort of background noise could affect these results. But again, LXC is much more efficient than VMs for networking. So if you still want to set up SR-IOV on your network card, here's how to do it. Now first off, IOMMU comes into effect for SR-IOV just as it does with normal PCIe pass-through. So the device you're going to be passing through needs to be on its own IOMMU group. You have to enable IOMMU in the kernel and also ACS on your chipset if it supports it. If you're using a PCI switch or chipset which does not support ACS, then those lanes will not be able to be used for the network card that you're doing pass-through with. In my case, my chipset doesn't support it, so I can use CPU direct lanes, but not chipset lanes. So I have an AMD system, so I added AMD IOMMU is on, and IOMMU is passed through to the kernel command line. Proxmox has docs on how to do this. So next up, I need to find the name of my network card, and I happen to know it's ENXG0 because I named it that. I have a blog post link up here if you want to rename your network cards to predictable things based on the MAC addresses. I've done that, so mine is named ENXG0. It would probably otherwise be called something like ENP1, F0, F1 or something. So now we need to enable SR-IOV, so we echo the number of VFs we want to make. So I'm going to make 6 in this case, just for testing. And we echo that to sys class net and then the name of our Ethernet device. So mine is ENXG0, and then device, and then SR-IOV num VFs. All the commands are in the blog post, link down below if you need them. So now after that, I get a bunch of new network cards. So ENP1, S0, F0, V0. So they got a V0 on the end for the virtual function. So in SR-IOV terminology, the PF, or the physical function, is the master card. So this is the NIC we already have in the system using its existing name. The VFs, or virtual functions, are more limited in their feature set, and these are the cards we get to pass to virtual machines. But there's nothing stopping us from initializing all of these virtual functions on the host as well if we wanted to use them for, say, like an LXC container. So now that I have these virtual functions, I can go over to my VM and just kind of add them. So I could go ahead and delete that network device that I was using for testing, and I'll instead add a PCI device. And in this case, we're going to use a raw device for now, so here's my virtual functions on the ConnectX-4. In this case, I'll add .2, seems like a reasonable choice. We're going to make sure we do not check all functions. I also don't check primary GPU because it's not a GPU. And there we go. So now it came up here as ENS16. So you can see it loaded the MLX5 core driver, and it's ready to go. And there we go. We got transfers working at pretty high speed. We can also use the resource mappings. If we go to data center resource mappings, we can add PCI devices. So we'll call this, so I only have one node in the cluster, we'll call that MegaLab. And I can choose which device that corresponds to. So I can pick all the virtual functions here, and let's go ahead and create that. So back over here, instead of raw device, I would choose mapped device. And I can say I want a MLX5 VF. So if you use mapped devices like I did, then the VMs will use whichever virtual function they have available first. So I set all 6 of my VFs available. I can create multiple VMs now. I'll choose that same map device. They'll choose any one that's free. It's perfect for this case. So for LXC, it's a little bit different. I'm editing the configuration file, so 542.conf. And I've added these lines right here. So LXC AppArmor profile unconfined, and then LXC net, and then these options here. So type is physical. It's off of ENP1 S0 F0 V2, so it's the second virtual function, and it has an IP address. So am I going to run out and switch all of my Proxmox systems to SR-IOV for my high-speed NICs? No, I'm not going to switch any of them. So first of all, the Ugreen NAS that runs my sort of home production stuff, I probably have a video up here on that, that has a 2.5 gig Intel i226, which does not support SR-IOV, and it has a 10 gig Aquantia Marvell NIC, which also does not support SR-IOV, so that's not going to happen. My box PC has the Intel X520, the Supermicro clone, and the Mellanox ConnectX-4 25 gig card. And both of those do support SR-IOV, but I could only use SR-IOV on the Mellanox card because the other slot comes off the chipset, and the chipset doesn't support ACS. So I could get a new board that supports ACS, new CPU that supports ACS. This is part of a limitation of the mobile CPU and desktop platform. The real desktop CPUs do support ACS. But anyway, the data didn't really show that it was that worth it for me. A lot of my traffic flows between VMs and containers. And so, I mean, you build that infrastructure, you have like a database, you have a proxy, things like that. But we're running in separate instances and talking to each other. And a lot of that traffic's not going out over the NIC. And where SR-IOV really shines is where that traffic is all going out onto the network. So if I had a bunch of customer VMs and I was hosting like hosting provider, then maybe I'd be looking a lot more at using SR-IOV because none of my VMs are talking to each other. They're all going out to the internet. Now, another thing to mention is that I use almost exclusively LXCs. I mean, I have VMs too, but I do a lot of LXCs. And those are just way more efficient at networking in general and don't really need the very, very slight efficiency gain they get from the SR-IOV NIC. Now, again, this is at 10 gig. All of my networking hardware is 10 gig. I don't have the hardware to go beyond 25 gig. I only have one 25 gig card. That's why I couldn't do 25 gig testing here. If I was at 25 gig, 50 gig, 100 gig, I'd probably be looking a lot harder at SR-IOV, trying to pinch out 5 or 10% at 100 gig. It's a big difference compared to pinching out 5% at 10 gig. Also, the tooling is just not there, at least for LXCs. For LXCs, you have to manually edit the config file, pick a specific virtual function, and half the time it doesn't rename it correctly. So when you pass the Ethernet device into the container, Proxmox renames it for some reason, and it often fails to rename it either there or back, which is really irritating. VMs don't have that problem. VMs, you can use mapped devices, so I could put all 127 VFs in a single group, pass that through, that'd be nice. Then I lose the ability to do VLANs, so I could set up a hook script to call IP links at VLAN. There's a IP command in IP route 2 to set the VLAN ID on a virtual function and let the network card do VLAN tagging for you, which is nice, but then I have to write scripts to set that up. I guess I could set up VF groups, so I have like 32 in a mapped group for each VLAN, and I just take one out of that group. Something like that, whatever. It's much more hassle than just using Proxmox SDN and doing it in software. Now that's of course at my bandwidth. I'm not a hosting provider, so my bandwidth is mostly going east-west within the system, not out of the system. So those are my use cases, not yours. If your use case sends a lot of data, more than 25 gigs of data, out of the system, you might want to look at SR-IOV for your VMs. If you're using Windows, you probably want to either install Broadcom's VMXNet 3 drivers or get off VMXNet 3 because it sucks. Now again, I could install Broadcom's drivers because they wouldn't give them to me. So those are my conclusions. Feel free to argue about them in the comments. I love when you guys do that. If you want to chat with me personally, link down below to my Discord server. I love talking to people about networking, Linux, Proxmox, that kind of stuff. Just no Windows admin, please. I don't do Active Directory. If you like my content and want to give me a tip, I would greatly appreciate that. Link to my Ko-fi down below. Thanks to Ugreen for sponsoring this video, and as always, I'll see you guys on the next adventure.